Hi class, this is your physics lesson for Monday, September 28th. I want to talk a little bit more about displacement and velocity and then go into a little bit more about position versus time graphs and velocity versus time graphs. I want to see how you can read one of those and understand how to make the other. All right, so a quick review. Remember, definition of displacement. We define displacement as the distance between the initial and final positions. Just simply the distance between the initial and final positions. It does not depend on what happens in between. So I use the example of somebody running around a track, right? If you start your race and you run one lap around the track and you stop where you've started, then your displacement is zero. Your distance you've traveled was 400 meters, but the displacement is zero because your starting and final positions are the same place. So now that's what I'm saying, but it means it doesn't depend on what happens in between. Now note also that displacement has a direction, right? So we can talk about that you moved 40 meters to the north or 40 meters to the south, right? So it has a direction. And oftentimes we will call one direction positive and the other negative. So oftentimes positive, for example, will be north and negative would be south, okay? So how do we write our equation? Simply delta x. Remember that triangle we call delta, and it means change in. Delta x equals x final minus x initial. Let's do a couple quick problems just as a refresher. Here we've got a x0 of minus 8 and xf of negative 17. Now note x0 and xi I'll use interchangeably, I apologize. But delta x then, right, we use our equation, is xf, which is negative 17. And we have to subtract a negative 8. And what do we get left with? A negative 9. Remember, if you subtract a negative number, that's the same thing as adding a positive number. So negative 17 plus 8 gives you negative 9. Let's do another one. So a bear starts at a position of 35, undergoes a displacement of negative 30. What is the bear's final position? So we need to rearrange our equation here because we need to solve it for xf. I'm sorry, I have a vf there, but we need to solve it for xf. So how do we solve this? We start with our original equation here in blue, delta x equals xf minus xi. We have to add xi to both sides, so we get xf by itself. That's what I've indicated here in green. And then what's our final formula? xf equals delta x plus xi. Okay. So let's plug in the values that they gave us in the problem. Negative 30 is our delta x, our displacement. 35 was our starting position. So we have to add those two together. And what's your final answer? It's 5. Notice that it's a positive 5, right? So the bear is still on the positive direction from what we defined as our origin. Let's look at another one. A woman undergoes a displacement of 22 centimeters and ends up at a position of negative 48. Where did she start from? Well, kind of like before, we've got to rearrange our equation. We need to solve it for VI. Here we go. We start with our initial equation, delta x equals xf minus xi. If we want to get that xi by itself, we got to subtract xf from both sides. And that's going to give us a negative xi equals a delta x minus xf. Well, to get rid of that negative, right, we multiply both sides by negative 1. And our final equation is simply xi equals xf minus delta x. Let's plug in our values. We were giving an xf of negative 48. We're given a displacement, a delta x, of 22. So negative 48 minus, remember our formula has a minus here, negative 48 minus 22 gives you a negative 26. And another one here, it's giving us the xf and the delta x, solves us from figuring it out. We don't have to go through the English part here to figure it out. We can just write in our values, right? Xi equals xf minus delta x. Plug in your values of 10 and 3, and we end up with an initial position of 7. All right. Hopefully that was a quick review. It made sense. Let's move on to velocity. Remember, we have a definition for our average velocity was simply our delta x divided by time. Our delta x divided by time. Let's do a few problems for that one. Train travels 300 miles in 6 hours. So we have a delta x, 300. We have a time, 6 hours. Plug it into our equation, right? Straightforward. Plug it right into our equation. 300 miles divided by 6 hours. We're going 50 miles per hour. Now, normally I would like to write this as miles and then put the division sign and then in hours, but this is one of those weird things where we have an acronym already for mph to indicate miles per hour. I'm just trying to use one terms we're familiar with. Another problem, a hammer falls from a height of 10 meters to a height of 3 meters. So we have what? A starting height, we have an ending height, and it fell over a period of 2 seconds. So we have a starting height, ending height, and a 2-second duration. So let's start off with our equation again, V equals delta x over t. Well, we got to figure out what delta x is. If hopefully you remember, delta x is simply x final minus x initial. We plug in our t is 2 seconds. Now let's plug in our values for our x final and x initial. And our final height was 3, our initial height was 10. 3 minus 10, up here in the top, 3 meters minus 10 meters, we still have 2 seconds in the bottom. Plug that in and you're going to end up with a -7 on meters on the top, 2 seconds on the bottom. So our velocity is -3.5 meters per second. Now, if you ever want to just kind of do a gut check, you realize, okay, our velocity is negative. That better mean that our ending point is below. It's in a negative direction from our beginning point. And indeed, you see going from 10 meters to 3 meters, you're going in a negative direction, which corresponds to our negative velocity. So we made our math correct. We didn't make a simple error. Now, just like with the displacement equation, we can rearrange our velocity equation. I'm not going to show the math here. This is what we've been doing. We've been doing this off and on for the last few days. So I'm just going to write down the answer. If you don't remember how to solve for this, try a little bit on yourself. And if you still don't remember, give me an email and I'd be happy to talk with you a little bit more. Now let's use the other 2 forms of our velocity equation. So we got our original velocity equation. We have one solved for delta x and we have one solved for t. Car drives at 70 miles an hour for 3.5 hours. So we have a velocity, we have a time, we're asking for its displacement, it's delta x. Well, we remember from the previous page, our delta x is velocity times time. Plug in our variables, 70 miles an hour times 3.5 hours. You've gone 245 miles. The jet flies east. So let's call east our positive direction. It flies east for 5 hours at 700 meters per second. Its initial position was 40 miles east of Chicago. What is its final position? Well, this last part here kind of gives us an idea of our origin. Our initial position was 40 miles east of Chicago. So we're going to assume Chicago's our origin. Our xi here is 40 miles to the east. Well, we go back to we're asking for final position. So we know somehow we've got to figure out what delta x is, because that's the only way we can get a final position into our answer. So let's start with our delta x. Delta x equals velocity times time. We were given those, right? 700 meters per second in 5 hours. Now we're trying to get to miles though. So we have some conversions here. And I also want you to notice that the velocity is in meters per second, but our time is in hours. So we have a lot of conversions to do here. Let's first convert our hours to seconds. So if we're going to convert the hours to seconds, how do we do that? We multiply by 60 minutes in an hour, and then our hours here are going to cancel our hours there. Then we have to multiply again by 60 minutes, 60 seconds over a minute. So our minutes are going to cancel here with those minutes there. And now our seconds here that's left on the right side is going to cancel with the seconds over here on the left. Now we have no units at this point in time except for meters, but we're asked to get miles. So we need to put a conversion term in here from miles to meters. Well, if you look that one up, you can see that that's 0.000621 miles in 1 meter. So again, we have our original problem, 700 meters per second times 5 hours. We have to do some conversions here to get our time units right. We have to do another conversion here to get our distance unit right, because we're asked for miles and we were given meters. Plug them all in and you get 7,824.6 miles. Now, one more step. Now we know what our delta x is. We were asked to find its final position. And our formula for delta x, xf minus xi, we got to rearrange it, right? We're looking for our final position. We rearrange it. We're going to see xf is delta x plus xi. Plug in our values, right? We just figured out delta x up here, 7824.6. We were given our initial position of 40, so we add those two together, and we see that our final position is 7864.6. It's positive, which means east, right? We define east to be our positive direction here. Car drives south for 50 miles per hour for 2.5 hours. That's easy enough. We like those units. They're consistent. Its final position is 20 miles north of Westerville. What was its starting position? All right. So we're asked for its starting position. That means we got to figure out what delta x is. We're going to start with our equation here. Delta x equals velocity times time. Let's plug it in. Negative 50 miles an hour. Well, why is it negative? What direction is our car traveling? South. Normally, we think of south as being a negative direction, north being a positive direction. So we have a negative 50 miles an hour for our velocity. We traveled for 2.5 hours. We ended up at a position, our displacement is negative 125 miles. Right, so we moved down. Our displacement is in a negative direction. Now we have to find our initial position, right? We started with our original equation. Delta x is xf minus xi. We arrange that to solve for xi. We see that it's xi equals xf minus delta x. Plug in your numbers. Xf was 20 miles, right, in a positive direction. It's north, so we have a positive 20. What was its final position? What was its initial position? We got to subtract out that displacement. Remember, our displacement was negative to begin with, so we're going to subtract a negative. Same thing as adding a positive, and we have a displacement of initial position of 145 miles. Now, I could have been done there because I had a positive, and we usually choose positive to be our north direction. But you could also just have explicitly said 145 miles north, because that would also be consistent with the wording of our problem. Either answer works. Just got to make sure you know which direction is positive, which direction is negative. Okay. Now, again, if I said 145 miles south, I wouldn't need to put that negative in because the south is telling us the direction. The south would tell us the direction is the negative direction. If I don't have a south or a north, then the sign tells you positive means north, negative means south. So let's finally get to our position and our velocity graph. Well, I'm hoping you remember from last week, right? If we look at a position versus velocity graph, if we have the PT graph, how do you figure out velocity? It's simply the slope of this graph. Simply the slope of this graph. So let's do some practice problems. I'm going to ask you to draw the corresponding velocity graph for each position graph. So let's scroll down here a little bit so I can get it all on the screen. What does this tell you about your velocity? What's the slope of this line here? Right, it's a horizontal line, so our slope is 0. So the first part here, we're going to have our velocity is going to be 0 for this part. Now let's look at the slope in our next leg. Let's look at the slope in our next leg. And I'll define a leg as where the direction here changes. Right? This is not a straight line, another straight line, another straight line. So a leg is just simply a line segment. What's our slope here? Well, we were going down 1, 2, 3, 4. So we went down 4, and we only went over 2. So our slope, again, is going to be negative 4 because we went down over 2. Our slope is going to be negative 2. So if our slope is negative 2, where should we put our velocity line? Let's put it at negative 2. And finally, for the last leg, what do we have here? 1, 2, 3, 4 is our x. Our y is still going down, so it's going to be negative. We went down 1, 2. So we went down negative 2. We went negative 2 for y, 4 for x. That's negative 1/2 will be your velocity for that last part. And like that, we've taken a position curve and we've drawn the corresponding velocity curve just by looking at slopes. Let's do another one. Here we have a graph, 1, 2, 3, 4, 5, 6. So we went up 6, and it took us 2 to get there. 6 over 2 tells you we have a slope of 3. So let's put a slope of 3 down here on our velocity graph. Now we have a slope that's going the other way. It's going down, so we know it's going to be negative. How far down did we go? 1, 2, 3, 4. How long did it take us to get there? 1, 2, 3, 4. So our slope here is simply negative 1. So on our velocity graph, we're going to draw a line at negative 1. Now, well, let me get there in a second. Let's go to this next one. Our slope is 0 here. right? So that means we have no velocity. We're not moving. So this part here is going to be just a line at 0. And finally, our last one, 1, 2, 3, 4. We went up 4, and it took us 2 units to get there. Our slope will be 2. Now, I haven't talked about this, but I'm going to lead into it soon. If you look at each segment here in our position graph, right, these are line segments, they're straight line segments. So what does that tell you? That means the slope is constant along this line. The slope is constant along this line. The slope is constant along this line. Well, if the slope is constant, that means the velocity is constant. And that's why our velocity pieces here are simply straight lines themselves, right? Horizontal lines. They're constant. They're horizontal lines with a 0 slope. Again, right? Constant, straight line, slope is constant. Our velocity is constant. How's our velocity constant? That means it has the same value. It'll be just a horizontal line at that value. Okay. I want to contrast that when we talk about acceleration soon. Let's look at our next part of this. Our next part tells us to draw the corresponding position graph for each velocity graph given. Now further says, I had this guy didn't disappear on me. It further says that our initial position is 2 meters. So we're going to assume we're starting at 2 meters. So we know right away we're starting at 2 meters. And it's a positive 2, so we're going up. Let's look at our velocity graph. Here we have a velocity. It's at 1. So we have a positive 1 velocity, and we're going for 2 tick marks. All right. So we started here at 2. We have a velocity went up 1. We went up 2. And our positive velocity, remember, we're going away from our origin, going above our origin by a rate of 1. 1. Well, what happens after that? We see that our velocity here, all of a sudden, it changes to -1. Wow, that's pretty odd. And how long there? For two tick marks as well. So now we've drawn our line here. It's got a -1 slope, right? Because our velocity here was at -1. Now we go to our next little line segment here. Now our velocity now is -2. So our slope changes to -2. So this section here, it's going to go down 2. Over 1, there's our slope of -2. Next part again. Here we have a line. Again, it's horizontal line. Means our velocity is constant. We are at 1, 2, 3. So we have a velocity of 3. And we're going to do that velocity for 3 seconds. So here's our line. We go up 1, 2, 3 in the first second. 1, 2, 3 in the second second. 1, 2, 3 in the third second. And finally, at the end here, we see that our velocity is 0. So we're just going to stay put where we are. And we're going to end up with just a horizontal line for that last piece. Okay. So when we're going from velocity to position, what you got to know is where are you starting? And we were told to start at 2 meters. Now, what's our velocity there? Well, that means we have to look at the value. Go to your velocity curve. What's the value? Our velocity is 1. That means our slope in our position graph is 1. So we have to draw a line with a slope 1. Here again, our velocity is a -1 for its value. So our slope better have a -1 in our position graph. Velocity here is a -2. That means our position graph should have a slope of -2. All we're doing is reading off our slopes and drawing lines to match that. So let's do one more here. Again, we're going to start at 2. We're going to start at 2, and I realized I didn't draw my lines in the right place. So we're going to start at 2. Our velocity is 0. So I'm going to take this first line here, and I got to move him now. So let's see if it'll let me move it. Right. We said we would start at 2. We're going at a velocity of 0. Right. Our velocity here is a value of 0. So we're not going anywhere. So we're going to draw a horizontal line. Then our velocity suddenly changes to 1. So that means our slope on our PT graph had to be 1. So again, I'm going to have to play with this guy a little bit, move him around. Whoop. See if I can grab it. All right. So now we have a slope of 1. Right? Our velocity has a value of 1. That means our PT graph has a slope of 1. You see we have our line here with a slope of 1 till we get to the next line segment. At that point, we see that our velocity has a value of 0, which means we have a slope of 0. So let's see if I can find this guy down here. There he is. Now we got to move him up. Again, see, I forgot to start my line in the right place. I have to shift everything up. Right? Negative 0 velocity here means we're going to have a flat line in your PT graph. And then finally, we're going to end up down here. Our last leg has a velocity of -2. So that means our PT graph, that line has a slope of -2. Let's go ahead and bring him up. And now I'm going to have to move him. Again, I made that offset wrong in the very first step. Okay. Find our velocity, draw a line with that slope. Find our velocity, draw a line with that slope. That's how easy it is to go from velocity to position time. All right, guys, we'll continue working with these a little bit more tomorrow. I've given you enough here. Hopefully this is making sense.